In today's video, we're going to look at the angle identities for sums and differences for sine and cosine, and also the double angle identities, and look at a couple of applications. So we'll start with the sum and difference angle identities. Now, if I have sine of the sum of two angles, it would be convenient if this would equal the sine of the first plus the sine of the second. However, that does not occur. The identity for this, to make this a congruent statement, is to take the sine of the first times the cosine of the second plus the sine of the second times the cosine of the first. So we don't distribute sine to both the angles. This is the actual calculation that will make this statement on the right side equivalent to the statement on the left side. Now, if we have the difference between two angles, as you might expect, the similar formula comes up, except we have a subtraction sign between here. So this would be the sine of the first times the cosine of the second minus the sine of the second times the cosine of the first. Now we have another identity for cosine, and it looks very different. If we have cosine of the sum of two angles, we don't take cosine of the first plus cosine of the second. It's not a distributive property. It ends up, the identity that works for this function is to take the cosine of the first angle times the cosine of the second angle minus the sine of the first angle times the sine of the second angle. So if this is an addition sign for the sum of angles identity for cosine, it actually is the difference between two quantities. If I have the difference between two angles, then I take the cosine of the first times the cosine of the second, and as you might expect, this is plus the sine of the first times the sine of the second. Now, we're not going to prove these identities. These are just identities that we need to remember. Now, a double angle identity is there are a couple of identities that come about quite frequently in calculus. And the first one is if I look at what happens if I have sine of twice an angle. I'm going to write it in terms of theta this time. So this identity comes up quite frequently in calculus, so we need to know this one. This is definitely one you should remember. And we can actually prove this by using our identity from up above. We can think of 2 theta as the sine of theta plus theta. And then that would tell us that we take the sine of the first times the cosine of the second, which happens to be the same as the first, plus the sine of the second times the cosine of the first. And therefore, these two functions are exactly the same thing. We're adding one of them here and one of them there, so we have 2 of them. So the sine of the double angle theta, or sine of 2 theta, is equal to 2 sine of theta times the cosine of theta. And this is an identity we need to remember. So that's called the double angle identity for sine. The double angle identity for cosine looks like this: cosine of 2 theta. And once again, we can prove what the formula is using our formula from up above, that the cosine of 2 theta would be cosine of theta plus theta. And when I take the identity for summing two angles, I take the cosine of the first times the cosine of the second minus the sine of the first times the sine of the second. And so if we simplify that, we find the double angle identity for cosine is cosine of theta times cosine of theta, which we can write as cosine squared of theta, minus sine of theta times sine of theta, which we can rewrite as sine squared of theta. So those are 2 identities we need to remember: the double angle identity for sine, the double angle identity for cosine. Now let's look at a couple of examples of using these identities. So in our first one, we're going to use our difference angle identity in order to find the cosine of 15 degrees exactly. Previously, we were never able to find the cosine of 15 degrees. That wasn't a reference triangle that we have some ratios memorized on the unit circle. But I know that the cosine of 15 degrees would be the same as the cosine of the difference of 45 degrees minus 30 degrees, because 45 minus 30 is equivalent to 15. Now if we apply the identity, we know the identity says if this is a difference, I'll have the sum of a couple of products, and I take the cosine of the first times the cosine of the second plus the sine of the first times the sine of the second. And so now if I do some simplification, I know that this is equivalent to square root of 2 over 2. Looking at my unit circle, I know that the cosine of 30 degrees is square root of 3 over 2. Sine of 45 degrees is my square root of 2 over 2. And my sine of 30 degrees is 1/2. And then when I simplify those values out, multiplying this together, I get the square root of 6 plus square root of 2 all over 4. And so that is the cosine of 15 degrees. Now likewise, I can figure out what the sine of an unusual angle is. Sine of 105 degrees. 105 degrees would be equivalent to 60 degrees plus 45 degrees. So if I figure out the sine of the sum of these two angles, I can determine what the sine of 105 degrees is. So this is not a particular angle that we've had to know in the past, but now we have a way of being able to calculate an exact value for this. So we know that this sine function, when we have a sum, takes the sine of the first times the cosine of the second plus the sine of the second times the cosine of the first. And now if we go through and substitute our different values here, we know that this value has square root of 3 over 2 as its quantity. This one is square root of 2 over 2. Sine of 45 degrees, square root of 2 over 2. And cosine of 60 degrees, when we look at the unit circle, is equivalent to 1/2. And then when we simplify this, we get square root of 6 plus square root of 2 all over 4. So it ends up, the cosine of 15 degrees ends up having the same functional value as the sine of 105 degrees. Now you can go through and do number 7 as well on your own by looking at the cosine of 95 degrees as being the sum of these two. Doing that on your own, you should be able to arrive at negative square root of 2 minus the square root of 6 over 4, and I'll leave that for you to use the function. Again, when you have an addition sign here, we would have cosine of the first times cosine of the second minus sine of the first times sine of the second. All right, so that's using our sum and difference angle identities. Now, I can ask you also on a question to use your double angle identity to evaluate some type of an expression. So if I said in a directions to use the double angle identity to find an exact value for sine of 600 degrees, I would need to think of the sine of 600 degrees as being the sine of double angle, some angle doubled, which would be 2 times 300 degrees. Now the double angle identity for sine would mean to take 2 times the sine of the single angle times the cosine of the single angle, which tells me that if I evaluate this, I have 2. If you draw this as a reference triangle, you'll find out that the reference angle on this is 60 degrees. It's in the 4th quadrant, and this would end up having a value of negative square root of 3 over 2. The cosine in the 4th quadrant, on the other hand, is positive, and this would have a reference angle of 6 degrees as well, but the x-coordinate would be 1/2. And when we simplify this all out, we would end up getting negative square root of 3 over 2. So if I refer to a double angle identity, that means I'm going to rewrite this angle in terms of 2 times a particular angle. Normally when we're using double angle identities, truthfully, it's in reference to having the angle in some type of a variable notation, but this is just showing that if you hit a sine of 600 on your calculator in degree mode, that you would get the same answer as if you multiplied 2 times the sine of 300 times the cosine of 300 degrees. Likewise, we can use a double angle identity to evaluate this. Now I know we know how to figure out the cosine of 120 degrees without using an identity, but just verifying that the identity does in fact work is what we're showing here. So I know if I want to show the identity works, the cosine of 120 degrees would be cosine of 2 times 60 degrees. Now the double angle identity for cosine looks very different. Cosine squared of 60 degrees minus sine squared of 60 degrees is what our double angle identity would say is an equivalent expression. Now we may want to rewrite that and take that square and put it up into this position to make it a little easier to evaluate. Now the cosine of 60 degrees, when we use the unit circle, becomes 1/2. The sine of 60 degrees is the square root of 3 over 2. And if we do some arithmetic, we find out that this will equal negative 1/2, which again, we did have the ability of figuring out the cosine of 120 just with a regular reference triangle, but this theorem will hold true for every single angle, that the cosine of twice an angle will equal the cosine squared of the single angle minus the sine squared of the single angle. Now this is the case where we normally have the double angle identities being used, is in the realm of some type of an equation. So if I'm trying to prove or verify this identity, notice now I have a situation in which I have a tooth theta here, so I would have to end up using a double angle identity of some sort in order to be able to prove this identity is true. So I look at my left side of my equation and my right side of my equation. I definitely would want to do some simplification and work on the left side to make it equal the right side. Notice that the 2 tangent of theta has a single angle. There is no double angle here. It's a single angle. So I want to do algebra and some trigonometric substitution in order to make the left side become 2 times the tangent of theta. So I know I can right away do a double angle substitution if I so choose for the numerator, and I can substitute in place of sine of 2 theta, 2 sine theta, cosine theta. I'm also going to do a substitution in the denominator. The denominator is equivalent to, with Pythagorean identity, cosine squared of theta. Put my little question mark. And I actually have 2 reasons for what I did here. I used the double angle identity for sine. I also used a Pythagorean identity. If you want to do that in 2 steps, you may. Now, my next step, I need to do some simplifying. I know that cosine will reduce one of these cosines out, and I'll have 2 sine of theta over cosine of theta is equal to question mark and put the ditto marks down. Now you can call that either algebra, or you can call it simplifying, reducing fractions. Any of those reasons would be fine. And now finally, I can see that my sine of theta over cosine of theta will equal the tangent of theta by the tangent identity. And I'm done proving my theorem. Okay, so remember on the identities, you only want to work with one side to make the one side equivalent to the other side. And that's all for today's video.